This chapter starts with a case study about fish. We're going to skip talking about this case study because we're going to come back to it to practice FRQ writing. So you can read it if you want to. You don't have to yet, though. So we're starting on this page. It is page 118. So this first half of this page talks about measuring population size. It uses bluefin tuna as an example. So it ties it back to the case study a little bit. Essentially, in the wild, it's difficult to figure out how big a population is. So with things like that get eaten for food, a lot of data that we have related to the fish population actually comes from fishers. But that's a misleading number because if a fisherman is able to catch 100 fish in one trip, and then all of a sudden they have a harder time catching 100 fish, they just make their trip longer to still be able to catch 100 fish so they can still sell the same amount. So only relying on that gives biologists a false sense of population size. So yeah, the population's doing good. People are still catching the same number of fish. That's not always true. So there are other methods that scientists have developed. Recapture, mark and recapture is one of them, so that's mentioned right down here. Recapture studies. We know that the amount of this particular tuna that's in the wild has dropped drastically because all of a sudden people are starting to fish it. It is not a fish that people were super fond of and that was marketed highly until like the 60s. So in the last, oh gosh, that's almost 20 years now. Oh no, 60 years, sorry. My math is not working very well. Yeah, I know. I thought 60 and said 20. So, it's all good. It's all good. Back in high school, I was not in high school. I was in high school in like the 2000s. So I was born in 90, so I'm 28. That's on YouTube now forever because I'm posting this video. That's okay, I don't care. Okay. So there's nothing really to take as far as notes go here. This is just background information to help the chapter make more sense for what we're talking about. Okay. This particular section starts talking about math. How do we represent population growth with math? So you need to understand the definition or meaning of these symbols, capital N, lowercase r, lowercase t. So here's the example. If you think of an insect that reproduces quickly that people don't like, cockroaches, great example. So the initial time that you start would be T0. So at T0, the number of cockroaches you have is 2. The rate that they reproduce at is 10. So 10 times 2, you get 20 cockroaches. Cockroaches can reproduce every 3 months. At least that's what the information we're given if you read this. So the next time they all reproduce, we have the 20 cockroaches because that's how many we got after reproduction. They reproduce at a rate of 10, so 10 times 20 is 200. After another 3 months, now we're at T3, we have the 200 individuals times a rate of 10 still, we get 2,000 individuals. Do that again, you get 20,000. So after only, this is 3 months, 3 months, 3 months, 3 months, so a year, we have 20,000 cockroaches. That's a lot of cockroaches. It's wonderful. The math for this, you can write this out and do a chart, but if you have to do 10 generations, that's a little wieldy. It takes time, so there's a simpler way to do that. It looks like this equation. NT equals N0 times R to T. Okay, so N is the number of individuals, R is your rate of reproduction, T is time steps. So how long does it take to jump and have reproduction occur, and then how many of those do you get? Okay, so that's described here. NT equals N0 times R to the T. So you could get a problem that asks you to figure that out. You can always do the math this way, long way, but if you remember this, you can use this. Okay. So this is the cockroaches example, actually graphing it. This type of growth would be considered exponential growth. So you need to know the difference between exponential and logistic growth. Does that sound familiar at this point? Sort of, maybe. Okay, so exponential probably sounds more familiar than logistic growth because you're used to looking at an exponential graph. Logistic growth is called that because of the shape of the curve. So exponential growth is sometimes called a J curve because it looks like a letter J. Okay. Logistic growth is sometimes called an S curve because the shape gives you an S, and there's a graph of that on the next page. As far as exponential growth goes, you also need to know when we're talking about continuous change. So delta is the triangle symbol, but we can also just use D for delta. So delta N, the change in population size over a period of time. So if we're talking about how fast the population changes in 10 years, okay, you would take your starting population and you subtract that from the population at the end to find your change in number of individuals, and then you say how long it was, 10 years, 10 days, 100 years, is the same as your rate of change times the number of individuals. Okay, different way to find the math rather than having to write it all out. Okay, and that's looking at exponential growth and continuous growth. So this section describes that. Exponential growth is called a J-curve, so that looks kind of like this. I'll move this sideways. Okay, so when we're talking about exponential growth, there's a couple of other terms that you need to know. Carrying capacity, that's the idea that a population can only support so many individuals. So if you have too many individuals, you've overshot the carrying capacity. You have more than you should, so then you're going to have a dieback or a population crash, which means more individuals die than survive. So you're not going to get a bunch more reproduction. Your population growth actually decreases because more of them are dying. So this up and down cycle is sometimes called a boom and bust cycle. You may remember that from an economics class or from a social studies class. But this going up and down around carrying capacity is pretty common because organisms reproduce a lot when there's a lot of food and other resources. And then when there's not enough, rather than everything surviving and reproducing, things die. Okay, so that back and forth cycle should make sense. You could also call it an oscillation. That's what you need to know about exponential growth. The reason we get the crashes and the diebacks is because of limits like carrying capacity. So this section talks about that and defines those things. From here, this is an important math concept you need to know. You are going to get quick math problems to do when you're looking at population. One of them is doubling time. How long does it take for the population to double? It's called the rule of 70. You take 70 divided by your percent of change, so the percent growth in the population, that gives you how long it takes to double. So if the growth rate is 2%, we would take 70 divided by 2. That's 35 years. If the population's growing at a rate of 10%, 70 divided by 10 is 7. It only takes 7 years for the population to double. So if you know the growth rate of something, the percentage, you can figure out how long it will take for that population to double. If we're talking about the population quadrupling, that's doubling once and then doubling again. So you take 70 divided by 2 as 35 years if the rate's 2%. So then it would take 70 years for the population to quadruple. Does that make sense? Okay. The only reason this works is because it's an estimate, so it's not perfect. But you'll never be asked to find like the rate of it only increasing by a quarter, because that's not easy math. You don't have a calculator. So 70 divided by a percent is much easier than trying to do this for exponential growth. Okay. S-curve, logistic growth, that's on the next page. So it looks like this. It's called logistic growth because if you use a logarithmic graph, it would give you a curve that looks like this. It's also called an S-curve because if you're going to talk about one of the letters, S is the closest that it gets to. Okay, so J-curve versus X-curve. Logistic growth is growth that slows down as you get to carrying capacity. So in the right conditions, anything can experience exponential growth, but as it reaches carrying capacity, it's going to slow down. So if we graphed this over less time, initially it would look like exponential growth. With enough time, though, then it starts to look like logistic growth. Okay? Does that make sense? Okay. Math. But guess what? This math, I'm really not worried about you knowing because you're never going to be asked to do the math like this. So don't worry about it too much. It's pretty much doing calculations for logistic growth. But this is too complicated for you to be asked to remember. So there you go. Simplified math. You like it. Terms you need to know: density dependent and density independent. These are things that can slow growth rates in a population. So if something is density dependent, it means that as you get more and more individuals, that factor affects the population more. So things like having enough food, having enough water, having enough space, those are density dependent. A density independent factor is something like a natural disaster, something that's a disturbance that happens that's going to affect the population, whether there are a lot of them or very few of them. Okay. R and K selected species. This one's fun. It's pretty easy to remember the difference between the two. We are a K selected species. We have long lives, we mature later, we have usually few offspring. R selected species have a short life, so they grow quickly. They produce lots and lots and lots of offspring. So things like insects are usually R selected because one insect can lay like hundreds of eggs, but then they die. Insects live for a year, maybe a day, depending on the insect. Fireflies, you know how they glow at night? They only glow like for one night. They have 24 hours to find a mate and lay an egg, then they die. So that's really short compared to humans. We take 18 years before we start thinking about maybe marriage, maybe. Okay, it takes a long time. It's a big investment.
The Firefly, Princess and the Frog survived for a while though.
Yeah, so it's not, you know, scientifically accurate there. Bad Disney. Bad Disney. Okay, you should be able to give examples of R and K selected species. And these are, this is a good chart for understanding the difference between the two. Okay, so you want to go back at this chart and look at this. If we're talking about population growth, there are 4 things that tend to impact population size, and it's BIDE, B-I-D-E. Births, immigration, so coming into a country, deaths, and emigration, things leaving a population. Okay, that's pretty straightforward, so you don't need a whole lot of information about that. These are just 4 things that contribute to population growth. So if you have 10 people who are born, but 2 people leave the country every year or leave the population every year, your population growth is different than if everybody stays. Okay? Same with deaths and emigration, same thing. Case study about deer. You should read this and see if you can apply some of the information that you've just been reading about earlier in the chapter. Okay, there are lots of deer though. I didn't know that people didn't used to know what deer were. About a century ago, no one had seen a deer because the population was so small. It doubles pretty quickly, so there are quite a few of them now. Survivorship curves. Okay, so this is an example of a survivorship curve. We're going to do a lab this week. Was it? Yeah, it was actually. We're going to do a lab this week related to this. If we are a K-selected species, like us, or elephants, for example, this is our curve. It's a type 1 curve. Okay, type 3 curve, this one is for an R-selected species. So what kind of species fits this B curve, type 2? What do you think?
Dogs.
Here's the example they give. Seagulls. They just die at random.
Dogs don't live.
Rodents are another thing that fit here. Dogs don't live that long, but they do reproduce kind of often. So dogs might fit in here. I'd have to look it up because I really don't know for sure. But the idea of this survivorship curve that's here is that things kind of die at random. So they can live longer, or if they're hit by a car or eaten by something, they die. Okay. Yeah, that made me jump.
Doesn't that fit humans though?
Okay, doesn't that fit humans? We're not as likely to die though. Okay, I'm going to pause it here.